네, 박건우 씨 안녕하세요. 네, 한성민 씨 안녕하세요. 네, 정상복 씨는 아직 안 오셨나요? 네, 알겠습니다. 정상복 씨는 늦는 걸로 생각을 하고 시작을 하도록 하겠습니다. 자, 혹시 뭐 어려움 같은 게 있었으면 얘기를 해주시겠어요? 박건우 씨와 한성민 씨. 숙제를 하는데 어려움은 없었나요? 음, 자, 네, 한성민 씨 질문 좋고요. 자, 한번 보도록 합시다. 그러니까, 음, 자, 제가 지금 한성민 씨의 결과를 보고 있고요. 지금 그런데 제가 풀라고 한 문제가 이거였나요? 음, 그렇죠, 그렇죠. 이게 지금 스트럭처가 이렇게 돼 있는데, 아, 지금요, 한성민 씨가 푼 건요, 1차원 시스템이 아니지 않습니까? 그러니까 무슨 얘기냐면, 우리가 수업 시간에 다룬 거는 완전한 1차원 상태에서 디락 델타의 형태로 퍼터베이션을 주는 거를 생각을 하고 있었어요. 그런데 지금 한성민 씨가 푸신 건 2차원 소자를, 물론 호모지니어스하죠. 하지만 2차원 소자에 대해서, 2차원 구조에 대해서 생각을 했고, 그 다음에 x가 x 델타 괄호 열고 x 마이너스 x 낫이라고 이렇게 되어 있는데, 그 말은 소스가 1차원으로 따지고 보면 한 지점에 들어간 게 아니라 2차원 상에서의 한 지점에서 들어갔을 거라는 거죠. 제 말이 맞나요? 어때요, 한성민 씨? 제 말이 들리나요, 지금? 어, 지금, 네네. 그러니까 이 결과는 어찌 보면 너무 당연한 거고요. 지금 그 전에 생각했었던 결과는 뭐냐면 1차원 시스템이라고 생각하고 거기에 디락 델타를 넣은 것입니다. 지금은 2차원에서 디락 델타를 넣었으니까 거기서 이제 그 디락 델타를 넣었을 때의 반응은 1차원일 때하고 당연히 다르게 되겠죠. 이해가 되시나요? 그러니까 이걸 1차원에 대해서 푸셔야지만 그 전에 우리가 얘기했었던 원하는 결과를 얻을 수 있을 거고요. 지금 2차원 결과를 보면은 당연히 어떻게 생각을 할 수 있냐면, 이제 다시 돌아가 볼까요? 요렇게. 자, 요렇게 있는 상황이잖아요. 요렇게. 그 전에 우리가 다루었던 건 1차원 구조였고, 1차원 구조에서 어떤 x 낫이라는 점이 있어서 이 점에서부터 이렇게 결과가 뻗어나가는 거였습니다. 결국 이해를 하시겠지만 요거하고 플럭스를 사용을 하면, 그러니까 요 두 개의 플럭스가 있을 거 아니에요? 이 플럭스의 차이가 결국 유니티가 되게 돼 있어요. 그리고 여기서는 당연히 1차원이기 때문에 여기선 직선이고 여기선 직선이 나오는 게 맞을 겁니다. 왜냐면 다른 부분에서는 라플라스 이퀘이션을 풀어야 되니까요. 자, 그러니까 이건 어떻게 생각할 수 있냐면, 차지가 하나가 들어갔을 때 거기에서 포텐셜이 어떻게 바뀌느냐라는 문제가 되는데, 지금 한성민 씨가 여기다 점 전화를 하나 준 거라고요. 점 전화를 주고 여기를 그라운드로 놓고 여기도 그라운드로 놓고 거기서의 전화 분포를 보고 있는 것이니까 이게 이렇게 당연히 직선 형태로 나타날 수가 없는 거죠. 네, 그건 뭐 너무 자명한 것 같고요. 따라서 이 문제를 제대로 풀고 싶으시면 오히려 차원을 줄여서 1차원으로 가져가서 풀어보셔야 된다라는 겁니다. 한성민 씨는 이해가 되셨나요? 네네. 자, 그리고 박건우 씨 같은 경우에는 그린 펑션을 포함하는 G 표현과 그린 펑션에서 어떤 의미인지 여기 뒷부분을 좀 다시 설명을 해 주시겠어요? 그린 펑션을 표현하는 G 표현과 그린 펑션에서 어떤 의미인지 궁금합니다가 어떻게 연결이 되는 거죠? 음, 네. 우리가 오늘 이번에 배웠었던, 그렇죠. 좋아요. 이렇게 해가지고 라플라스 방정식을 우리가 그렇죠. 풀었었고 1차원이었으니까 그냥 명시적으로 1차원으로 써볼까요? 이거를 어떻게 했었냐면 요 방정식을 풀었었습니다. x제곱이 이렇게 라고 풀었는데, 사실 그리고는 if i를 이렇게 얘기를 했지만 이거는 사실 이 함수 fi는 지금 네, 정상묵 씨 지각입니다. 자, 그래서 요 파이는 뭐죠? 그냥 이렇게 파이라고 쓰기보다는 이게 그린 펑션이라는 걸 표현을 하기 위해서, 그래서 보통은 이렇게 쓰곤 하죠. 그린 펑션은 당연히 x의 함수죠. 솔루션이니까. 그런데 이렇게만 쓰게 되면 이게 언제 어느 조건 하에서 구해진 그린 펑션인지를 알 수가 없어서 사람들이 보통 여기다 표시를 하나를 더 붙여주곤 해요. 이렇게 컴마라고 하기도 하고 어떤 때는 세미콜론을 쓰기도 하는데 이렇게 x 낫 아니면 g x, x 낫 이렇게 쓰곤 합니다. 자, 그런데 여기서 말하는 이 x 낫이라는 거는 어떤 주어져 있는 지금 상황에서는 주어져 있는 위치에 해당하는 것이고 그래서 실제로는 x의 함수인 거예요. x 낫은 파라미터에 불과합니다. 소스의 위치 이렇게 생각을 해줄 수가 있고요. 결국 그래서 우리가 지난번에 신나게 풀었던 그 파이는 도대체 뭡니까? 라고 말하면 그건 제가 요 표기를 도입하는 것을 늦추기 위해 가지고 이렇게 한 것이고 이 그린 펑션이라고 이렇게 말을 할 수가 있겠습니다. 자, 박건우 씨가 이해가 되셨나요? 아니면 뭔가 또 다른 질문 같은 게 있을 수 있으니까 질문을 또 해주시고요. 네, 알겠습니다. 자, 그러면 뭐 이 정도로 하면 될까요? 더 추가적인 질문 있으시면 질문해 주시고요. 자, 정상복 씨도 뭐 추가적인 질문이 있나요? 이 숙제를 풀면서 홈워크를 풀면서 어려움이 있었는지 묻고 싶네요. 보니까 박건우 씨도 똑같이 2차원으로 푸셨군요. 네. 2차원으로 풀면, 뭐, 아니, 사실은 2차원으로 푸는 게 이제 더 일반적인 방법입니다만, 그렇지만 먼저 1차원으로 푸는 거를 해보셨으면 좋겠네요. 네. 역시, 지금 정상목 씨 것도 보고 있는데, 정상목 씨의 것도 이렇게, 나타난다. 그렇군요. 자. 자, 이거는, 네. 알겠습니다. 지금 하고 있는 것들이 1차원에 대한 얘기였으니까 1차원으로, 우리가 왜냐면 신나게 그걸 풀었잖아요. 그 신나게 1차원에서 풀었잖아요. 그러니까 그렇게 해놓고선 비교를 2차원에서 되고 안 맞는다고 할 수는 없겠죠. 여러분들이 푼 건 어떤 거냐면 이런 거라고요. 자, 제가 여러분 보고 풀라고 했었던 건 요거였는데 이걸 만약에 여러분들이 2차원 도메인으로 바꾼다면 어떻게 바꿔야 될 거냐면 이렇게 바꿔야 될 거라고요. 이렇게 제곱 더하기 이제 이렇게가 들어가겠죠. y에 대한 이기미분이 들어갈 텐데 이거는 호모지니어스 하기 때문에 이 부분은 실제로는 사라지게 될 거고 그 다음에 여기에 그냥 디락 델타를 쓰게 될 것입니다. 요게 2차원에서 여러분들이 구한다고 하면 얻어지게 되는 꼴일 텐데 그걸 어떻게 해석을 하셨냐면 디락 델타니까 여기다 요걸 더 붙일까 해가지고 특정 어떤 y 값을 정해가지고 요렇게 했다는 거죠. 그러니까 저런 결과가 얻어졌다고 할 수가 있겠습니다. 자, 무슨 얘기인지 아시겠죠? 그러니까 완전한 1차원을 별도의 코드를 짜가지고 해보시면은 결과가 똑같이 나오는 것을 아실 수 있을 겁니다. Okay, so now since you have done your homework, so we will move to lecture 20. So continuing the discussion about our green function. Okay. It seems that seems like that. So my tablet is now showing some difficulty to response to my writing. Anyway, so let's extend our previous lecture content to the multidimensional. But multidimensional case, actually, you have done it quite well, actually, all of you. So I wanted to extend it to multi-equation case. So in the last lecture, we have thought about the green function. So the equation, the original equation was the Laplace equation. Laplace equation has one single variable, and yes, so now it can be written as x comma x naught. Of course, if we extend it to multi-dimensional one, then phi, originally as a function of x, can be written as a vector r, and also here we have g and r naught. So that is the equation or the green function we can consider in the case of a Laplace equation. So I'm afraid that we are now experiencing certain delay, but anyway, although it is not so fast, so eventually you will hear my voice. So I will just keep the lecture. So, however, this is just a case of our Laplace equation, and what we wanted to calculate is actually drift diffusion model. So that is the one we wanted to analyze and we wanted to utilize. So instead of this Laplace equation, how can I extend it to a more general case? In this case, Laplace equation is one equation, yes. However, in the case of drift diffusion, in this case, actually we have Poisson equation and electron continuity equation and Hall continuity equation. So let's say that we wanted to introduce certain Dirac delta function into this drift diffusion model. Then we have to say, there is a certain Dirac delta source inside this drift diffusion model. But question is, when we introduce such kind of source term, where should it be inserted? For example, Poisson equation, or electron continuity, or Hall continuity. Which one should be the right place for our Dirac delta function? That is my question. So how about your opinion? So of course, some of you can say that since we are working with more or less electron dominate device called MOSFET and MOSFET, or sometimes a PMOSFET. But anyway, we can clearly identify the major carrier type. So maybe in the case of N MOSFET, the seemingly most important one would be this electron continuity. Yes, you are right. However, in general sense, if we are talking about, for example, really a PN junction whose doping density is more or less the same, then what is the most important one we have to consider? So we cannot say electron continuity equation is more important than hole continuity, or Poisson equation is more important than other continuity equation. We cannot say so. So unfortunately, we have to consider all three cases. So think about this analogy. So now we have a certain two-terminal device. So yes, here you have 1 and 2. In this case, if we have just two terminals, then we can define y parameter. So you know y parameter is just given by okay, so sorry about that. So my tablet shows some difficulty. So let me just try to fix the problem. Okay, I just introduce a new pencil. Okay. So anyway, let's just go to this two-terminal case. Then we can define y parameters. So y parameters for alpha and beta, of course beta and alpha can be either 1 or 2. So in this case, the y parameter is defined as what? D I alpha over round V beta. So this is the definition of our y parameter for a pair of terminals alpha and beta. So observation is related with terminal alpha, and perturbation is inserted for terminal beta. So we will have this form. Yes, however, if you have really this two-terminal device, so usually you don't care about it much. So usually what you have is Y22. Why do we have Y22? So it is simply because, you know, when we have beta, so think about this one. So if we have one, 2, then what is it? This is nothing but, here we have 1, 2. But you know that in the case of this two-terminal device, we have the conservation of some of our terminal current. So simply speaking, I1 is just minus times I2. So yes, this is just the way we can proceed. So now this one exactly equal to Y22 minus. Okay, So, are you with me? Simply speaking, if we have this simple two-terminal case, then every quantity y parameters can be obtained from this y parameter, single y parameter. So why am I introducing this kind of really obvious thing? Let's think about now three-terminal case. If we have three terminals and say this is 1 and 2 and 3, then things become more complicated. For example, yes, let's compare this y2 2 and y3 2. So can you make any relation between these two quantities? For example, I3 over round V2. And now we have to consider here I2 and I3. However, the only information we know about them is sum of I1, I2, and I3 should be 0. So once we know I2, however, we cannot determine the value of I3. So that is still unknown. So we cannot find the immediate result. So let's come back to our green function case. Yes, if we have just one equation, then we can just consider only one case for inserting Dirac delta into our equation, the only equation. But now we have three different equations, so we have to, unfortunately, we have to introduce the Dirac delta function into each of our equations. So now you can think about this one. You can think about the green function. Okay, something is wrong. So I think that this tablet is not working properly any longer. So well, I will just okay. So let's think about this one. R not and R. Then now you can think that there is one green function where the Dirac delta function is inserted into the Poisson equation. And also you can think that there can be another green function where Dirac delta function is inserted into our electron continuity equation. Also, you can find another one like the Dirac delta function is inserted into your whole continuity equation. So you have to consider three different cases. So are you all with me? So if you understand this situation, then please let me know. So then I will move to the next part of our discussion. So I'm afraid that today tablet is not working properly, and also YouTube is experiencing certain delay. So. Mhm. Okay. So Mr. Han, thank you. You asked me why we have to introduce three different equations. So it is obvious that we are now talking about drift diffusion model. So you know that drift diffusion model has three equations. So that's the reason why we have three equations. So could you please confirm that you now understand my answer? Or I will just write down in in this chatting log. Okay, so now you understand this situation is corresponding to three different oh okay, so uh, so when you consider drift diffusion model, then we have to consider Poisson equation and electron continuity equation and Hall continuity equation. Since we have three different equations, our Dirac delta function can be inserted any of them. So therefore the reaction of our unknown variables, electrostatic potential, electron density, hole density, can be quite much different when you insert somewhere something, and therefore we have to consider three different types of green functions. Okay, so green function where Poisson equation is perturbed, or green function where electron continuity equation is perturbed, or finally the whole continuity equation is perturbed. We have to think about three different cases. So now seems that now it is over, then now you can understand all of this one, but still we have something we have to keep in mind. So now we have different types of perturbation. So now we have R naught and R naught. So this Poisson equation, electron continuity equation, and Hall continuity equation, these pair equation and position, equation, position, equation, position, just to specify where we introduce this Dirac delta function. For example, if we have Poisson and R naught, then we introduce this Dirac delta function into Poisson equation. Yes, quite intuitively, electron and Hall cases can be considered in the same way. That is the case, and now we have the observation point here, R and R and R. Then Now, natural question is, what is the physical quantity or unknown variable observed at R? So, what is this G when Poisson equation is perturbed? Think about this one. Let's say that we have a certain device and this point. Okay, so unfortunately my tablet is now dying. Okay, so here we have R lot where the source is injected, and now we say that okay, in the case of Poisson equation, what is the perturbation? If we introduce Dirac delta into our Poisson equation, then that is corresponding to insertion of a certain charge into our system. If a charge is inserted there, then obviously there will be certain impact of this charge injection. Okay, we will just introduce a certain charge, fixed charge into it, and electric field will be changed. Also, hole density, electron density will be modified. And now say that we are saying certain situation, this point is observation point. Oh, sorry, not we have to write down in this way. Yes, make another mistakes. Once again, R. Yes, this is observation point. Observation point, and this is excitation. Then question is, what is the observed value? Do you measure potential, or do you measure electron density, or do you measure hole density? Which one is measured in this point? Okay, so pair of Poisson equation and R not just to satisfy, we will insert a certain charge at position R not. It's okay. And observation point R specify, we will observe certain quantity at position R. But which quantity is measured or observed in this situation? For example, you just calculate or measure phi, or you can measure n, or you can measure hole density. Of course, you can easily understand they can be quite much different, because of course potential and densities, they are basically different quantities. And even in the case of electron continuity, electron density and hole density, depending on the electric field, the internal electric field, we can have quite much different reactions of those parameters. So my conclusion is so simple. Green function in this generalized situation has two position indices, so R naught and R. This is corresponding to, this second one is excitation, and this first one is observation. Then we have to also specify here two things. Which equation and which variable. Okay. 어, So now you understand this case. So basically, when we consider this multi-equation case, your green function should be generalized in that sense. Previously, green function was just a function of excitation position and observation position, R and R naught. That is still true. However, if we have multiple equations and multiple variables, then we have to specify which equation is excited and which variable is observed. So, for example, I wanted to say this way: z phi phi. What is it? This means that Poisson equation is perturbed and we are now observing something like electrostatic potential. For example, also we can find this one. What is the meaning of this quantity? Now, still the same perturbation is applied. However, instead of electrostatic potential, we just measure the response of our electron density. Also, finally, we can define this quantity. Now, we are observing the whole density. And we can proceed with different perturbations. For example, phi n. Sorry, because my tablet is really dying now. Okay, yes. For example, now you can understand all quantities in this first law is corresponding to the observation variable phi. However, now perturbation is different. The first one is corresponding to perturbed Poisson equation, and second one is perturbed electron continuity equation, and third one is corresponding to the perturbed whole continuity equation. Since equations are different, their responses can be quite much different. So we cannot assume any kind of equivalence between these components. So of course we can think about this one, GNN and GPP, and yes, we can think that this one and this one. This, although they look similar, however, this means that when whole continuity is perturbed, what will happen to the electrons? Or when electron continuity is perturbed, what will happen to whole continuity equation? That is the physical meaning of those quantities, and obviously, in general, they cannot be the same. Okay, so up to now, I just spent almost 30 minutes to explain. In the case of multiple equations, we have to consider a generalized version of our green function. So why do we have the generalization? Since we have multiple equations to be perturbed and multiple variables to be observed, so we have to consider a pair of variable and equation, although the positions are the same. Okay, so this is the first thing I want to deliver in this lecture. So please confirm that you have, all of you have understood my lecture up to now. Or if you have any question, then please let me know. Okay, good. Okay, so no. Please, Mr. Park. So let me just refine your question. Potential is not perturbed. So in this case, this phi should be considered as potential is perturbed. It's not a correct wording. I wanted to say Poisson equation is perturbed. That would be the correct wording. So think about, you are now asking the meaning of this quantity. For example, in this case, the Poisson equation is perturbed. For example, think about this one. The Poisson equation is written as this form: d minus equal to 0. This is the Poisson equation. Of course, we are now talking about the small signal analysis. So this general form of Poisson equation is not used. So instead of that, we just adopt, for example, electrostatic approximation and minus q times hole density, electron density, and d. So this is the Poisson equation. Yes, this is just the Poisson equation written under the electrostatic approximation. Yes, this is the Poisson equation still. And perturbed Poisson equation just looks like this. Now we will write down this way. Here we have phi, and here we have the position. Previously we had phi, but now it should be written as green function. The observation variable is phi, and Poisson equation is perturbed, and it is R and R naught. Of course, this gradient operator is working only on the first position variable R, so you can just treat this R naught as a parameter. So, and when you go to the second term, here we have a minus q, and previously it was p. However, it should be written as g p phi. So still observation variable is whole. However, this whole is induced by the perturbation in the Poisson equation. Still we have R and R naught. And here we have also something like G and phi and R naught. And we don't have anything related with this doping density because, please note that we are still working in the small signal scene. So this term should not appear at all. So this is the left hand side, and right hand side we have delta R minus R naught. This is the Poisson equation, the perturbed Poisson equation. Yes, this is the perturbed Poisson equation, and the quantities appearing in these perturbed Poisson equations are, yes, they are green functions. However, there was the position for electrostatic potential and position for hole density and electron density. That's the reason why we have to introduce different green functions for those variables. Okay, Mr. Park. So I just wrote the perturbed Poisson equation with green functions. So I hope that this is more clear to you now. So if you have a further question, then please let me know. Your question is quite reasonable, and yes, so it makes the discussion more clear. So okay, you have another question. Okay, yes. So, but please note that this GN phi, this GN phi can be also used in the case of a Poisson continuity equation. Okay, so good. Let me just clearly write down all of these one in a form of or equation. So I'm afraid that my pencil is not working properly any longer, but anyhow, let me just write down rigorously. Okay. So think about the general equations. The general equations just looks like this. Yes, this is the equation, the Poisson equation, and round n round t minus 1 over q and j n. That is the electron continuity equation, and let us consider whole continuity equation. Sorry, this is positive and j p. Yes, that will be the general equations. And how about the small signal equation? If we go to the small signal equations, then quite easily you can say this is corresponding to here Q. I mean that small signal one. Small signal here should be written with not exactly phi, but we have to consider delta phi, the response of electrostatic potential, and small change in our hole density and electron density. Yes, this is the small signal form of our Poisson equation. And how about the small signal form of our electron continuity equation? In this case, we have j omega and delta n corresponding to our round n over round t term, and now we have 1 over q and divergence of delta Jn, that will be 0. And obviously here we have quite a similar equation corresponding to whole continuity equation. Delta Jp equal to 0. So all of you understand this today we have many difficulties and many mistakes, but anyhow we have to proceed. So I have no idea how can I delete this ruler once it is appearing in the screen. So well, just place there. Okay, then now so well, anybody have any question about this small signal one? So this is general equation, and this is small signal equation. Of course, this one with solved with the boundary condition. So we have applied a certain boundary condition, certain voltage excitation to certain terminal. That's the reason why we have non-zero values for our small signal response. So that is the situation we have studied up to now. And to be more concrete, so I wanted to introduce even further discussion about here. Now we have j omega delta n and minus 1 over q, and let me just write down this delta jn. What is the jn in general? Jn in general can be written as q mu n n and gradient of phi plus q dn gradient of n. If we consider this mobility and diffusivity as constants, then we can easily understand this delta jn should be written as q mu n, it is constant, and delta n and phi. However, this is just DC component, and minus q mu n, now n, however, it's a DC component, and gradient of delta phi plus q dn gradient of delta n equal to 0. This is nothing but I just introduced one specific realization of our delta n vector. Yes, just I wrote it in that way, and I will just continue the same thing here, j omega delta p plus 1 over q, and here we have divergence. And divergence, in the case of a whole current density, the only thing we have to care is the different sign for diffusion term. So I will just write down immediately mu p delta p and gradient of DC potential, and q mu p and p dc gradient of delta phi. Finally, we have minus q dp, yes, we will have this form for small signal, really small signal equation. That was already covered in your previous implementation for AC analysis. You have done it. But point is now, as Mr. Park asked, so what is actually doing? What is actually done in the case of green function? So let's think about the case where we introduce a perturbed Poisson equation. Now, in the case of a perturbed Poisson equation, instead of this 0, we introduce delta r minus r naught. So then the quantities appearing here as a delta phi here and delta phi here and delta phi here should be changed to what? So our previous delta phi in this case should be written as g and phi and r naught. In the same way, so let me just repeat it again. If we have delta p here, then this delta p is here and also here and there. Those quantities should be written as g p phi r naught. Yes, now you understand what is going on. Finally, if we have delta n, and we have to say this delta n, and delta n should be written as g n phi r naught. Okay, so this is the explicitly written form of Mr. Park's question. So yes, simply speaking, I want to say that previously I just show you the Poisson equation only. However, in reality, we have to consider all of three equations, and every delta phi or every delta n, every delta p should be changed to g phi phi or g p phi and g n phi, because this is the general notation. However, please note that this is only the case when we insert this Dirac delta function into our Poisson equation. Of course, we can think about different cases instead of this one. Now, we can introduce the perturbation in electron continuity equation. Then what will happen? The green function is newly introduced. However, in this case, instead of this g phi phi, p phi, g p phi and g n phi, we have to write down g phi n, g p n, g n n. Finally, I know that all of you already understand this one. If we introduce this Dirac delta function into whole continuity equation, then we have to p and p and p for our quantities. So, Mr. Park, so I just elaborated to explicitly show everything for our green functions depending on the situation of a perturbed equation. So can you understand my explanation? So I think that now it is clear to where we have to introduce which green function. Okay, then now let me just announce your homework today. So your homework is today is quite simple. Quite simple means that just calculate all of these green functions. You can think about three different, actually nine different equations. Oh, sorry, not equation, nine different green functions. So please arbitrarily select your observation point, observation point are not. Then you can perturb your Poisson equation. Then you will have the solution vector which contains g phi phi g n phi g p phi. Yes, you will, once you solve the AC system, this green function system once, then you will have a vector containing all of g phi phi, g n phi, and g p phi. Then please, yes, draw it. Then of course this is the case you perturb the Poisson equation. Then you can change your type of perturbation. Electron continuity is perturbed, then you will have a vector containing g phi n, g n n, g p n. Then just draw it. Then you will have all of the solution. So are you with me? Simply speaking, I'm just asking you one straightforward routine to calculate your green function. So I think that once you have done your AC simulation properly, then that is not that difficult to consider this green function calculation. Simply speaking, in a discretized form, it simply means that you just insert one unity to your right hand side in your matrix equation. So all other quantities are zero in your residue vector, so-called, in a sense. Then just insert one single number 1 into certain position and just calculate the response of your system. That will be the green function. Okay. So do you have any question about homework number, what is it? Homework number 20? So of course, what should be your device? Which device? Which bias point? So that is the question. And I wanted to just recommend you to use your usual device on the, used in your calculation. So for example, if you have used double gate MOSFET, then please use double gate MOSFET. And bias condition, yes, starting from equilibrium case, consider many different bias points. Yes, Mr. Han, you're right. So you have to calculate three different cases, like your three equations. Each of your three equations is perturbed, and then you will get just responses of your all three variables, and each of them has its own symbol, like a G phi phi, G n phi, or GP phi. So please make it. And although homework number 20 is designed for certain device of your interest, but I wanted to strongly recommend you to, before starting, the application to the double gate MOSFET. First of all, think about just a homogeneous bar. So once your device simulation is working properly, or green function calculation is working properly for your homogeneous bar system, then please extend it to more complicated system like for example PN junction, or for example double gate MOSFET, or any kind of system you wanted to simulate. Okay, so are you with me? So do you all understand my suggestion? So if you have any question on homework number 20, then please leave your message. Or if you have understood homework number 20, then please confirm that you all have understood the meaning of homework, the problem in homework number 20. Then I will wrap up today's lecture. Okay, you are right. This is the ruler, and I wanted to eliminate it. But oh, okay, thank you, Mr. Jung. So actually, I previously I tried, but it did not work. So I was not able to eliminate the ruler once it appears in the screen. But thank you, thank you. And any other question about the homework or lecture contents? Okay, so Mr. Park, you're right. So as you know, um, first of all, I wanted to say green function should be regarded as the AC, a kind of AC analysis. So your equation, your perturbed equation, should be the linearized system, linearized equation. So simply speaking, you have done your AC simulation, and at that time you have made the linearized system, and that linearized system is a little bit perturbed by your Dirac delta function. Okay. Okay, good. Then I'm certain sure that this concept is not very easy to understand. So maybe in real implementation, you will have plenty of difficulties. Then please let me know through the Slack DM message. So, okay, then good luck to your homework number 20, and see you next Tuesday. Bye.